Okay, so we start. So good evening, everyone. So I think all of you have submitted homework, and I don't have any formatting errors so far. So just I have to grade it. I haven't graded it yet. Okay, so today I want to continue the chapter 4, logistic regression, and also the linear discriminant analysis. Do you have any questions so far for the materials last week or homework? Okay, I'm sharing this, the slides. So last time that we introduced logistic regression, so the idea is that we have the response variable y. So we want to fit this y on predictors x, maybe x1 to xp. But since y is just binary, that we only have two values, that if we fit the straight line, such as y is equal to beta naught plus beta 1 x1 plus beta pxp, then we have trouble because the y can take only 0 or 1. So the fitted line looks like this. But the fitted value of less than 0, or if we continue, fitted value more than 1 does not make much sense. So we have to have the something like this, the right-hand side. So we see that the probability of default is higher if probability of default is higher if the balance is higher. So the probability of default should the fitted probability of default should be should look like this, the blue line. So if the balance is low, probability is very close to 0, but that does not go below 0. So always some positive value. And also the balance is higher, the probability approaches to 1, but it never exceeds 1. So we want to fit this kind of curve. So the linear regression does not work, but we think about at first the probability of y is equal to 1, and given x. And this should be some function of this. So f is called link function. I think the f inverse is called link function. So we have f. The f is from real numbers to numbers between 0 and 1. So the f is called Logistic function in this case, and the exact form of f is f of x is equal to the e to the power x over 1 plus e to the power x, or we can say that the 1 over 1 plus e to the power negative x. So that means if x is very small, such as negative 100, the f of x is almost 0. And if x is really large, then this is almost e to the power x over e to the power x, for example, if x is 100. So fx approaches to 1. Yeah, so sometimes this model is written as just the f inverse of probability of y is equal to 1, maybe given x, is equal to the beta naught plus beta 1 x1 plus up to beta p xp. So in such a case, the f inverse of x is, you can get this as log of x over 1 minus x. So sometimes that we have this form. Log of x over 1 minus x is if x is very small, I mean the small close to 0, then the log of almost 0. So that is almost negative infinity. And if x is very close to 1, then log of, for example, 0.99 over 1 minus 0.99 is log of 99. That is a large number. So this F inverse is a map from 0, 1 to R. Right. So logistic regression, formulate the relationship between x and y in this form. So one notable difference is we have F, and also that we consider probability. So we don't have an error term. So probability is a kind of expectation, right? So we can say this as the expectation of y. So expectation of y, expectation of y is equal to 0.6, for example. Then if y is binary, y is equal to 1 with 60% probability, and y is equal to 0 with 40% probability. So probability is expectation. Since we have already taken expectation, we don't have an error term. So no error term, and we have link function. That is the difference between logistic regression and linear regression. And the linear regression interpretation is easier because the y is a linear function of x. So if we have increase of x1 by 1, then we have increase in y by beta 1. But for logistic regression, because of this function f, the relationship between y and x1 to xp are highly nonlinear. So if you want to interpret this coefficient beta 0 or beta 1, or maybe even beta 2, beta 3, and so on, we have to consider this slope as the slope for log of odds ratio. So p of x over 1 minus p of x is a kind of probability of y is equal to 1 over probability of y is equal to 0. So a kind of the success probability over failure probability. So the ratio of the probabilities. Yeah, so that is what we studied last time. And the estimating the regression coefficients. So remember that so what's the way to estimate the coefficients in linear model? I mean, if we have x and y here, and we have some scatter plot, and we have fitted line. How we determine this fitted line? What's the criterion to determine this fitted line? Maybe you have seen this even in a newspaper. How to determine this based on the plots? Anyone can remember?
Least squared, distance.
Yeah. Least square, yeah. So we measure the distance, vertical distance, right? Then we minimize it. So if this is epsilon 1, epsilon 2, epsilon 3, epsilon 4, epsilon 3 is negative, epsilon 5, epsilon 6, 7, 8. Then we minimize sum of epsilon I square. So minimize this sum of epsilon square. So that is the criterion. So least square. And obviously in logistic regression, we cannot use this method because it's highly nonlinear. So what should we do? Then we have to use the maximum likelihood. So if you have taken stat 5800, then probably you have studied this a lot. And 5030 we mentioned a little bit. So we just want to explain this again. We want to study this again. So what's the maximum likelihood? So the idea is that we see the probabilities in a different direction than usual way. So suppose we have the 3 dice, the x and y and the z, and we roll one of those dice, maybe once, and we got the result. Then based on the result, we want to see the which die that we rolled. So basically we have die x, y, and z, and we randomly picked up one and we rolled it. and we only see the result. We don't know whether the die is either X, Y, or Z. So, okay, so, and X, Y, and Z are different dies. And the X is usual fair die. Y is a loaded die with 1/2 probability for one and 1/10 probability for the others. And Z is also a loaded die, and with 1/2 probability, it gets the face of 2. And the one with 30% probability, and 3, 4, 5, 6 with only 5% probability. And suppose that the result is 2. Then you can see, you can compare this probability 1/6 and the 1/10 and the 1/2. Then you can see that this 1/2 is largest. So we can say that the Z is most likely we have chosen. So this is the way of the maximum likelihood. So usually in probability theory, just we focus on one probability space. So either first line or second line or third line. But maximum likelihood that we see this in a different direction. So we see this table vertically, and we compare these 3 values and see that the 1/2 is the largest. So Z is most likely. Yeah, so that can be extended for multiple observations. For example, suppose that the first trial, the result is 2. And the second trial, result is 1. And what's the likelihood for X, Y, and Z? Then first trial 2 and second trial 1. So the probability get the 2, then 1 is 1/36 for this the die X. So for this example, probability is 1/6 times 1/6, so 1/36. And Y, 1/2 times 1/10, so 1/2 times 1/10, so 1/20. And the die Z, the 3/10 times 1/2, so this is 3/20. So in this case, actually the die X is much more likely than the others. Sorry, yeah. So you can see this is much larger than the others. So in this way, we can calculate which die is most likely. So X, Y, Z are just the 3 possible choices in this case, but in general, this is a parameter. So parameter theta is either X, Y, or Z. Maybe I would say that the parameter is in the space of X, Y, and Z. But in general, this may be some continuous space. So in this way, we can estimate the parameter. So in this case, maybe parameter theta hat is equal to Z. So this is the idea of likelihood. So we see probability distribution in a different direction. Maybe we see the family of probability distribution in a different direction. And how to estimate the logistic regression by this maximum likelihood method? Okay, so last time, I think that you did a quiz to calculate probability from beta naught and beta 1. So you can, given parameter, we can calculate probability. We can calculate probability of Y is equal to 0. Or Y is equal to 1. Yeah. So given parameter, we can calculate the probability. And suppose that our observation Y's are maybe like the 0, 1, 0, 1. The X values are omitted, but the calculated probability of Y is equal to 1 is given as, for example, 0.2, 0.8, and 0.5, and 0.9. Okay, so this is a kind of reasonable model because when probability is higher, actually the Y is 1, and the lower probability is actually 0. Of course, it's better if we have closer to, the closer probability to 0 or 1. But in this case, we can calculate the likelihood as, okay, so at first, the this one, okay, so success probability is 0.2, and actually it failed. So we are a kind of 80% correct, right? So the y is equal to 1. Probability of y is equal to 1 is 0.2. That means the probability of y is equal to 0 is estimated as 0.8. Maybe the others 0.2, 0.5, 0.1. Okay, so the likelihood that we have to get this 0.8 or maybe 1 minus 0.2. Okay, and times second one. Actually, the success probability is 80%, and actually we succeed. So 0.8. And the third one, 0.5. Maybe I would say 1 minus 0.5. And the fourth one, we have 0.9. So if we failed, then we multiply the 1 minus probability of 1. And if we succeeded, then we multiply the probability of 1. So that is the likelihood function for this logistic regression. So to be exact, the given beta naught and beta 1, or maybe up to beta p, we can calculate probability of y is equal to 1. So for each value of maybe pair of beta naught and beta 1, we can calculate these probabilities, then likelihood. So I don't know this, like how much is this? 0.8 times 0.8 times 0.5 times 0.9. So 0.64 times 0.45. So this is approximately, I don't know, 2400 and the 2024. So 44, I don't know, and 20. So 286 or maybe 0.286, I don't know, but then we can calculate it. So then we change this value, then we can calculate likelihood again. And when likelihood is largest, then we can determine what's the best beta naught and beta 1. So if we write in the equation, the likelihood function becomes this way. So we multiply the probability of y is equal to 1. So remember that the p of x means the probability of y is equal to 1 given x. When y is equal to 1. And we multiply 1 minus the p of x, that when y is equal to 0. To be exact, probability of y is equal to 1 given x is calculated as this, and the 1 minus is this, right? Yeah, just you can see that the 1 minus this entire quantity becomes this. So this is the likelihood function, and clearly this is a function of, beta naught and beta 1. Right? So it's very complicated, the nonlinear function of beta naught and beta 1. So we can maximize this, then we can get the maximizer. So the computation is much more difficult than linear regression. Linear regression, we have just minimized the sum of squares. That is the summation of y I minus beta naught minus beta 1 xi square and I is equal to 1 to n. So this is just quadratic function of beta naught and beta 1. So you can immediately get the maximizer. Minimizer, sorry, minimizer. But to maximize this function, that we have to solve highly nonlinear maximization, optimization problem. So we maximize this likelihood. So in least square, we minimize this. So we are thinking about negative of the squared errors. So we maximize likelihood, we minimize the sum of squares. So we have the different direction. Yeah. And finally, once we optimize that quantity, that we can get the estimated the beta naught and beta 1. So estimated beta naught and beta 1 are here. So if we fit the probability of default, then we get this. So intercept negative 10.6, the balance, the coefficient for balance is 0.0055. And standard errors are here. So if we divide coefficient by standard error, then that is equal to the z statistic. And the negative 29.5 and 24.9. So this is similar to t-value. So if roughly speaking, it's more than 2, then it's statistically significant. I mean, absolute value is more than 2. So actually the p-value is very small. So yeah, so here, this ratio, the coefficient over standard error, does not follow t-distribution. So we are solving very highly nonlinear problem, so that we cannot use the t-distribution. So we have to rely on the fact that if sample size is large, then ratio that goes to the normal, standard normal. So if z statistic is more than 2, or to be exact, maybe more than 1.96, then we can say that it's statistically significant. So you can see that this one is positive. So the larger balance means larger default probability. So that is very important in interpretation. Do you have any questions? And the coefficient itself is not really easy to interpret. So just this means the balance is $1 higher, then log of odds ratio is higher by 0.0055. So it's a little bit hard to interpret the coefficient itself. And okay, so suppose that we have a new observation. Okay, so we fit the logistic regression with existing data here. And suppose that we have new observation, but we don't know this y naught. In such a case, that we can predict the probability of y is equal to 0 given x as this. Yeah, so just we use the fitted value. Yeah, so this is one example. So the intercept beta naught hat is here, and this is the slope for, I mean, the beta 1 coefficient for the balance. So if we have a new person, I mean the new data set, new data point with $1,000 balance, $1,000 debt, then default probability is calculated as this. And actually this is 0.00576. So only if we only know the balance of that, debt balance of that person, the default probability is 0.57%. So not very high, not very risky to lend money to him or her. Any questions so far? Okay, so next one is qualitative predictor. It's slightly maybe easier to understand what's happening. So suppose X is a qualitative predictor. For example, whether a person is student or not, or what's the blood type of the person, or what's the I don't know, the occupation in categorical variable, like something like that. Then we can use that in the prediction model and interpret in the logistic regression model. So suppose that we predict the whether the person is in default or not based on the student status. X is equal to 1 is that the person is a student, and X is equal to 0 if not. Then, okay, so estimated model is here. So what do you think? So the student has higher default probability or lower default probability than non-students?
Higher.
Sorry?
Higher.
Higher, yes, yeah, thank you. Yeah, it's higher, right? So if we have the positive coefficients, then it means the higher if student is yes. And how to interpret it? This model is relatively simple, so we can simply interpret by comparing the predicted probability for x is equal to 1 and x is equal to 0. If student x is equal to 1 and the default probability is 0.0432, so 4.3%. X is equal to 0, non-student, then default probability is 2.9%. So we can say that the students have 1.4% point higher default probability. I don't know what's the reason. Maybe students have lower income, maybe students are younger, or I don't know, maybe some other reasons. But at least if we only know this information, the students have higher default probability. Okay, but the usually we want to combine the information such as balance or student status or age or maybe the gender or something else. For credit score, I think the race is prohibited to use by the government. So we have some factors that we cannot use it. I don't know gender, but at least we have the multiple information such as balance, income, the student status, age, and so on. So usually we want to have the multiple factors such as x1 to xp. So we can get this model as multiple linear logistic regression. So the estimation is in the same way. We have 4 parameters in this case, but we can get these estimators by maximum likelihood estimation. So in this case, the default probability is explained by balance and income and student status. So in this case, we can see that the balance has positive coefficient. Higher balance means higher default probability. That's reasonable with high z-score, so significant. Income, positive. Higher income, maybe they borrow even more than the statistic lower. Yeah. So Americans, the people say that, I mean, in Asian countries, if you got the $1 million, they spend the $500,000 and save 500,000. Americans, if they get $1 million, then they use, the $2 million by, the borrowing $1 million more or something like that. So higher income, the higher default probability, that's possible. But actually the z-value is really small. So probably this is, we can say, very close to 0, we can say. So it's significant at all. And student status, this is interesting. We have negative coefficient 0.64. So that means if you're a student, actually the default probability is lower. So last time we don't have a balance. So we haven't enough information, but actually the balance is really important factor. And if we have already accounted for balance, additional information that the person is student, actually indicates a lower default probability. So negative is 2.74. So probably the student is also meaningful factor to determine default probability. Yeah, so these are significant. Any questions so far?
Yeah, I know you said it earlier, but can you repeat what the Z statistic tells us?
Z statistics tells us the significance of coefficient. So for example, this is 0.033, but it's statistically significant or not. So that is the explained by the Z statistic. To be exact, if coefficient is equal to 0, I mean, true coefficient is 0. If the true coefficient is 0, then the Z statistic is distributed as Z standard distribution. So standard normal distribution, maybe it looks terrible shape. Standard normal distribution have this shape, and we know that the negative 2 to 2 have almost 95% coverage. So for example, this statistic of negative 2.74 means that our test statistic falls in probably around here. So that is, the very strange if the true coefficient is 0. So we reject the possibility that beta 3 is equal to 0. Okay. So when we see this statistic, we can see how significant this coefficient is.
Yeah. Okay, thanks.
Yeah, sure. And for linear regression, that was the T distribution, but here the Z distribution, I mean the standard normal distribution. So Z means standard normal in statistics. Yeah, and the last time that we just compare the student and the non-student and the default probability. But here that we consider the default probability by student status and also balance. So we have seen that the balance is higher, default probability is higher. But also, if the person is a student, then default probability is slightly lower. So that means if student, the curve is this. So still balance is higher, default probability is lower. But if the balance is the same, then it's lower. It has the lower default probability than non-students. So if we fix the student status, that we can make this, curve. I don't really know why this is not a smooth logistic curve. Probably that is just because we don't have enough sample points here. You can see we evaluate the curve at 2000 and 1500, but in between we only have the two values. So maybe every 100, maybe $67 they plot. So that's why this is not smooth. And the dotted line, I'm not sure. And this is just one descriptive statistic, the student status, sorry, the credit card balance by student status. And actually, if student status is yes, then the credit card balance is higher. So basically, they don't have income, but they can expect the more income after graduation, so that they borrow a little more. So it looks students have higher default probability, but if we adjust balance, then actually the student has lower default probability. So students have typically maybe $1,000 deficit, and maybe for non-students, maybe $700 or something. So effectively, if we ignore balance, we are comparing the student with $1,000 debt and the non-student with $700 debt. So I don't know, this point on the red curve and this point on the blue curve or something like that. And actually the red curve slightly higher value. We cannot really see here, but that is what's happening exactly. Any questions so far? Okay, so consider that we have studied so remember that we have studied the residual plots for linear regression. So do you remember the residual plots for logistic regression? probably most answers are no. Right, so at least in 5030 that we haven't covered the residual plots for logistic regression. In 6840, the applied regression analysis, that we covered some kind of the the residual plots for logistic regression, but that is very detailed, the discussion of logistic regression. Usually that we don't consider the residual plots for logistic regression. And that is because the pattern of residual plot is entirely determined by the shape of logistic curve. So what does it mean? We can see the original the first figure of logistic regression. So this is a kind of scatter plot. So we have the fitted line, the blue one, and orange dots. That is actual plot. So what's the residual? Residual is between, the distance between plot and fitted curve. Maybe even. So this is the residual. Okay, so this is residual. This is residual. This is residual. These are residuals. Okay. And in terms of density, maybe about the x-axis, maybe we have more residuals around here, and we have more residuals around here. So that's true. But in terms of the shape of the residual plot, it's just totally determined by this blue line, because all dots are on y is equal to 1 and y is equal to 0. So once we determine the fitted curve, the residual plot is just the difference between 1 and this curve and 0 and this curve. So residual plot almost have the same shape for all distribution, all data. So that's why we don't use residual plots. One way to make a residual plot is maybe we consider bins. 0 to 500, 5 to 1000, 1000 to 1500, and so on. Then we can see the average, the fitted value, the average, the observations. So, for example, 0 to 500, the no person has in default. So that means the value is 0. But at the maybe 2000 to 2500, maybe 70%, 80% of people are in default. So that we have point here. So if we plot points around here, for example, like here and like here, then we can see the discrepancy between the fitted line and the dots. So if we summarize dots in some intervals, then we can get some meaningful residual plots, but otherwise we cannot say the residual plots. I mean, this is 0.1 if 90% of plots are y is equal to 0 and 10% y is equal to 1, then we can say we can plot the point at 0.1. In this way, if we have the binned plot, then we can give some meaning to the residual plot. But usually the logistic regression that we don't really consider the residual plot. So just that we see coefficients and maybe we see the prediction performance, but we don't really see the residual plots. Yeah, so that is the way the logistic regression works. So this means the appropriateness of logistic regression, logistic function F, the logistic function. Yeah, I'm always confused logistic and inverse logistic function. So logistic function is I think the one, the log of this part is the logistic function, and the 1 over 1 plus e to the power negative x is the inverse logistic function. Maybe not, sorry. The logistic, this is inverse logistic, sorry, inverse logistic. And And logistic curve is the e to the power x, 1 plus e to the power x. Yeah. So why we choose this function? Basically, this is because the likelihood function has the good shape. So if we use logistic regression, we can prove that the likelihood function is concave. So that is very strong property. So if we have the concave curve, so it's easy to optimize it. So it's easy to find the the maximizer. So that's why that we are using logistic regression. So if we use different function than this, then of course model is meaningful, but the estimation is slightly more complicated computationally. And elements of statistical learning. So this book is a little more advanced than our textbook. So this discusses the property of logistic regression pretty well, even compared to some statistical textbooks. Any questions so far? So next one is multinomial logistic regression. For example, we are thinking about categorization problem, maybe character recognition problem to categorize the handwritten digits to 0 to 9. We have 10 categories. Then we cannot use the logistic regression. We can use logistic regression if we only have, for example, 1 and 2, or we group it as 0, 6, 9 versus the 1, 2, 3. Then we can do logistic regression. But if we have multi-categories, 10 categories, we cannot apply logistic regression. So in such a case, the one extension is this multinomial logistic regression. So what's the way to do it? Okay, so suppose we have k classes, in this case, k is 10. So value of y is either 1, 2, 3, or k. Then the multinomial logistic regression formulates the relationship between y is equal to 1 to y is equal to k as this. Okay, so we consider the ratio of y is equal to I and probability of y is equal to k. So a kind of k is the baseline in this case. And we compare the probability of 1 and the probability of, probability of y is equal to 1 and the probability of y is equal to k. And 2 and the k, 3 and the k, up to k minus 1 to k. And for each of them, that we use the basically logistic regression. So we compare. This is basically the log odds ratio. Log odds ratio is equal to linear function of x1 to xp. Yeah. So this is the multinomial logistic regression. Yeah. So once we identify these, models, then we can calculate probability of y is equal to 1 to probability of y is equal to k. Right, so we have ratio. So suppose that, okay, so suppose that the log of p of y is equal to 1 over p of y is equal to 3 is equal to, okay, so suppose k is equal to 3, and this is equal to what? Maybe e, then the log of probability of y is equal to 2 over y is equal to 3 is equal to maybe e is not good, maybe 1 and 0. Then what we can say, then we can take the exponential of both sides. Then probability of y is equal to 1 over 3 is equal to e, right? So, and this means the probability of y is equal to 2 over probability of y is equal to 3 is equal to 1. So that means the probability of y is equal to 1 to 3. The ratio is, if this is 1, then 2 has the same probability, 1 has probability e. So that means the total is 2 plus e. So total probability should be 1. So that means the probability is E over E plus 2 for 1, and 1 over E plus 2 for 2, and 1 over E plus 2 for 3. Then total is 1, right? So that means if we have this and this, these two pieces of information, then we can calculate these probabilities. Right? So in this way, the multinomial logistic regression work. For example, suppose we have maybe how many predictors? Maybe 64 predictors for character recognition problem for numbers 0 to 9. How many parameters in total? I mean 10 categories and the 64 variables plus intercept. This is very practical setting, right? So maybe 8 by 8 digits, 8 dot by 8 dot images. Then maybe we have grayscale for each dot. Then we decide that what the number is. So in such a case that we fit the these characters, the response of 10 categories on 64 variables plus intercept. How many parameters in total in this model? Anyone? I will get maybe some special credits for this if you got the right answer. 64 predictors plus intercept. We have 10 categories. How many parameters in total? Anyone?
65.
Right. So 65, because for each model, we have 65 parameters. Oh, 65. Oh, no, actually not. No, sorry. No. Sorry. Close. You can correct it. Yeah. For each model, 65 parameters. So
650.
650 is what Antarang said, right?
Yeah.
You said 65 or?
I said 65.
Oh, 65. 65 is for each model, right? And 650, that's even closer, 650, but it's actually not. Remember, we have 10 categories. Maybe hint, if 2 categories, binary, how many parameters? That's just usual logistic regression. So
641.
641. No.
640.
Okay, so no. So just to think about the model, right? So we are taking ratio, right? So we have 3 groups. We have to compare probability of y is equal to 1 and the probability of y is equal to 3. And also 2 and 3. We have to have the 2 ratios to get all of these probabilities.
Is it 9 times 65?
Sorry, once again?
9 times 65.
Yes, you're right. So who said psi?
Yeah.
Yeah. So psi. Yes, that's right answer. So 65 times 9. I mean plus 2. Because what's the reason? So we have the 65, but we only have the 9 pairs, right? So we compare the probability of y is equal to 0 and y is equal to 1, right? And also probability of y is equal to 2 and 0, and 3 and 0, and up to 9 and 0. So if we take this, if we go to these 9 ratios, we can get the probability, right? Or we can say that the total of 10 probabilities should be 1. So we can only need the 9 pieces of information. Yes, so we have similar question to this in a quiz, today's quiz. So obviously the problem is we have too many parameters here. So if we have a large training set, for example, we have a data set with 1 million entries, then it's totally fine. But if we only have very small number of observations, for example, 1,000 even, that we may have trouble to estimate parameters because we have 65 times 9. So how many parameters? So the 540 plus 48, so 485 parameters, right? So at least we need like 2,000, 3,000 observations. Possibly that we need more. Yeah, so this idea is pretty natural if we think about the logistic regression as this log of px over 1 minus px, because this is probability of y is equal to 1, and this is probability of y is equal to 0. Maybe to be exact, given x value. Okay, so, but here that we compare the more ratios. So 1 to k, 2 to k, 3 to k, up to k minus 1 to k. So it's pretty natural extension of logistic regression, but many parameters. So we have to be careful. Yeah. We only need k minus 1 ratios because total probability is 1. And this can be fit by the multinom function in NNet package. So NNet is neural net, and the neural network is a kind of multi-layer of logistic regression. So that's why this function is in NNet package. Yeah. And the next one is the ordered logistic regression. So sometimes the response is categorical but ordered. So typically the rating, for example, movie rating from 1 to 5. Then 1, 2, 3, 4, 5. Maybe 1, 2, 3, 4, 5 is a little bit misleading. So maybe rating 1, rating 2, rating 3, rating 4, rating 5. So we have order. Also, we don't really know if these are in an equal interval. Maybe R1 is much more terrible than R2, but R2 and R3 are similar. That's possible. So at least we have order. Yeah. Yeah. Or you are, for example, doing something about, I don't know, order or something, right? So in many sports, for example, ranking is released. So we can order the observations. And suppose the response variable is ordered, not continuous, but ordered. Then what we can do? Of course, we can do multinomial logistic regression, but that ignores the order of the categories. So in such a case, that we can use the ordered logistic regression. We don't cover it in class, but just I wanna say that such a model exists. Yeah, so it's in a POLR function, and I would like to give you an image about what's the difference between multinomial logistic regression and ordered logistic regression. So multinomial, if we have 3 classes, then basically we compare three groups pairwise. Suppose we have this kind of observations. Maybe some observations difficult to distinguish. This is x1 and this maybe x2. Then, okay, so basically idea of multinomial regression is pairwise. So maybe we distinguish the groups. For example, distinguish the triangle and the squares by maybe this line. And also the triangle and the crosses by this line or something like that. This is the. So if we compare these two probabilities, then we can get the probability of the crosses across and the probability that each point belongs to the crosses or the triangles or the squares. So this is the idea of multinomial. And ordered logistic regression, they're more restrictive. Suppose we have x1 value and x2 value. These are predictors. Then it's ordered. So we expect that if one group is like this and the another group is like this, and the other group is like this. So we only allow the one direction, and we use the parallel lines to separate the triangle and the square and the crosses. So this is the this area, and this area. So parallel. So since this is ordered, we have more restrictive about the separating lines. So actually, the less number of coefficients. There's still more coefficients than binary linear regression because the boundary we have to decide. Right? So that makes more additional parameters. But the basic idea is this. Yeah, so we don't cover in detail, but we can still use it with this package. Yeah, so if ordered, then I think that usually ordered logistic regression that works better and they give a better interpretation. So if pairwise comparison, it's really difficult to interpret the coefficients. Maybe if only 3 categories and only 1 or 2 predictors, still we can interpret the coefficients. But if more than that, it's really hard to interpret the coefficients. But ordered logistic regression, almost similar to logistic regression, with some boundary information between 2 classes. So it has a better interpretation. So for application purpose, it's good. Yeah, so generally interpretation is really important. For example, in banks, we develop very complicated model to, predict the default. But if we cannot really interpret and just the computer returns this person has 15% default probability, but the person looks nice, to the human evaluator, then it's really hard to use that model. So interpretation is one key to be used practically. So ordered logistic regression, less number of parameters, so it's good. Any questions so far? Yeah. And alternative choices for logistic regression. So we have used the function f. So f is equal to this. So how about other choices? And the one notable property is that this is increasing function and it ranges from 0 to 1. So good function to replace f is CDF, cumulative distribution function. So cumulative distribution function, the natural choice is this normal CDF, standard normal, the distribution function. And if we use the standard normal distribution, the model is called probit model or probit regression. And it's famous fact that the this function, the inverse of this function, so phi inverse of y, so this does not have an analytical form. So if we want to get what, so probability, yeah, so we cannot really write the function of this inverse function. So this is quantile function, right? So given probability, what's the value of x? So that cannot be determined by the simple formula. So it's harder to deal with. But the normal distribution has some good properties, such as multivariate normal distribution. So so-called the multivariate logistic regression. That is, we have the y is the pair of numbers, like the 0, 1. Maybe first trial, the failure, and second trial succeed, or something like that. If y is multivariate, often the probit model is used because the multivariate distribution is simpler for logistic regression, the probit regression. Okay, so that's the way, and maybe we have some other choices like the arctangent. That's the we skip that for now. Or maybe also the coset distribution that has heavier tail than this. Usually logistic regression is more robust because logistic regression, actually the tail part is heavier. So does approach to 1, slower than the probit regression. So logistic, usually the more stable than probit. So next one, the linear discriminant analysis. So far, do you have any questions? Okay, so the next one is the linear discriminant analysis. So this is basically more stable than logistic regression, and especially when classes are well separated in the predictor space. So the logistic regression, the one problem when data is too good is that it's hard to determine the optimal line to separate two groups. So suppose that the one group is like this in the data set. This is x1 and x2, and the other group is like this. So it's totally separated. So it's easy to separate two groups perfectly. But in this case, what's the logistic? Logistic regression is basically we think about some separating line, and based on the height with respect to this line, that we decide the how strong, how much the probability is to belongs to this group and this group. Okay? So basically, we think about the projected height to this line to judge probability. So basically, it's similar to the determining the separating line for the two groups. But for logistic regression, it's hard to determine in this case because this is perfect separation, but also this is perfect separation, and also this is perfect separation. Even this is perfect separation. So we have so many the perfect separating line, all perfect separating lines. So it's hard to see which one the logistic regression will choose. And LDA is more stable than logistic regression. So we just explained the simple case that we only have one predictor. So LDA is basically based on the distribution of each group. So suppose P is equal to 1. So we only have X. Then one group, we have these observations, maybe like this. most observation around here, but maybe some observation here. And another group, maybe center is around here, but there may be some variation like this. Then we estimate the distribution of the circles and the crosses. So the distribution of circles, this is equal to the like this. Okay. Estimate some continuous distribution, and the red one, the probability, maybe just for explanation purpose, that we need a little wider probability. We have a little more overlap, so maybe we add some observations more. Okay, so the blue one, if we estimate the probability distribution, we have like this. And red one, we have distribution. Suppose we have more red points. Okay, we have more red points. Then more observation. So, sorry. Like this. Okay. Then the idea of linear discriminant analysis is to compare these probabilities. For example, that we cut off here. Suppose we have a new observation here. Then this height is suppose 2, and this height is suppose 8 or something. Then okay, so this is the y is equal to 0, and this is y is equal to 1. Then at this point, x naught, probability of y is equal to 0 given x naught is equal to 8/10. So 80%. And the probability of y is equal to 1 given x naught is 20%. Basically, we want to do this. And the multivariate distribution, then we have a little more complicated thing, but suppose that we have p is equal to 3, p is equal to 2, and this is only 2 groups, but suppose we have 3 groups, then how to do that? Then we think about the first group like this. And the second group, maybe triangles. Then we fit the contour plot for each of the groups. Maybe third group, maybe circle. Then, okay, so this one, so the crosses that we fit some contour like this. And the second one, we have another contour, triangle. And the third one, also we have another contour. And based on this, then we decide, based on the height of the contours, we decide which group the point belongs to. So for example, if we have the point around here, probably this is much closer to the center of this. So this point is more likely to be this group, red group. And probably this point is more likely to belongs to maybe group, black group, or possibly the blue one. So this is the idea of the linear discriminant analysis. So in this case, actually the higher separate, the well separated case, it's even easier to judge. Logistic regression is contradictive in the sense that the easily separable cases, the more difficult to estimate. So it's a little bit contradictive. Yeah, so that is the idea. If we say this mathematically, that we say that we estimate the distribution of predictor X for each class. Okay, so we make the distribution of X, right? Then they use Bayes' theorem to calculate this. So that is basically what we did in the previous slide. So based on this height and based on this height, that we decide what's the probability of these. So example, they want to classify animals into horses, the giraffes, and the deer by weight, height, and neck length. So the weight and height and neck length, so this is the three predictors, x1, x2, x3. And based on this, we have the three classes. So basically, y is equal to 1, and y is equal to 2, and y is equal to 3. So k is equal to 3. Yeah. And the Bayes theorem. So how to quantify, clearly explain how to calculate probability. So at first, we prepare the Bayes theorem. Probability of A given B is equal to probability of A intersection B divided by probability of B, right? And A intersection B is probability of A times probability of B given A, right? Yeah. So in this way, that we can prove this formula. Then how to calculate it? So suppose that the fk of x, so distribution of x for group y, so that is the weight distribution of horses, or weight distribution of giraffes, or weight distribution of deer. So that is the f sub k of x. K is equal to 1, 2, 3, horse and the giraffe and the deer. Yeah, so that is the f sub k of x. And also that we assigned pi k. For example, if you find the one animal in Michigan, then even if it has really long neck, then still you see that as a deer, right? So because we don't really have giraffes in Michigan. So we have the prior probability, pi sub k. Maybe we have horses, maybe in Michigan, maybe horse, maybe we have only 10% probability, and a giraffe, maybe we have only 1% probability, and a deer, maybe 89% probability or something like that. So we have these probabilities. So these affects, right, our judgment. So when I was living in Madison, Wisconsin, so there are many Koreans, but there are only few Japanese. And often I was talked by a stranger that, are you Korean? And that's reasonable because, okay, so based on some, face or some other characteristics that they judge, the nationality. But if you know that we have, for example, the 10,000 Koreans and only 500 Japanese, even if the one person looks Japanese, still, maybe it's a good guess to say he's a Korean, right? So this prior probability matters for the decision. So if we consider this f sub k of x and pi k, how we can calculate this? So given x value, given weight or given neck length, how to decide whether the animal is giraffe, deer, or horse. So okay, so at first we just apply the definition of the conditional probability here. Then we just decompose the numerator as the y is equal to k and probability of x is equal to x given y is equal to k, right? So just this is from the previous slide. And x is equal to x means x is given, but the y is unknown. So we consider all possible y, right? So, and take summation. Then that is the probability of x. Probability x is equal to x. That means the probability of x is equal to x and k is equal to, y is equal to 1, or y is equal to 2, y is equal to 3, right? So if we have 3 possible y, then if we add up these 3, then that is probability of x is equal to x. So we can say this. So we can calculate these probabilities as this. We have probability. So this is the prior probability. probability of horse, deer, giraffe unconditionally. And that is pi k. And also that this is the given species that we have the weight distribution. So we have the fk of x. And the denominator is just the summation of this over k. So we can calculate the probability of the the deer, horse, and the giraffe. And one quiz is similar to this. So this is the linear how linear discriminant analysis works. And from the next slide, we will discuss the more details about the linear discriminant analysis for specific case, one-dimensional case and a two-dimensional case. Do you have any questions? Okay, so if not, then that's it for today. So see you on Thursday.